provided a /C unit wiring configuration is not correct. The minimum circuit ampacity for the /C unit must be 15 amps, and the maximum circuit ampacity should not exceed 25 amps. This means the wiring and circuit protection must be appropriately sized to handle this range. The circuit breaker ampacity must be 25 amps or less to protect the circuit from overcurrents. The wire ampacity, referring to its current carrying capacity, must be 20 amps or more to safely handle the load. In the described setup, the circuit breaker ampacity is 20 amps, and the wire ampacity, using number 12 THHM wire, is also 20 amps. While the circuit breaker ampacity is less than or equal to the maximum circuit ampacity, and the wire ampacity is greater than or equal to the minimum circuit ampacity, there's a potential issue with the circuit breaker size relative to the /C unit's maximum ampacity. To ensure compliance and safety, several factors need to be considered in detail. Firstly, the motor nameplate must be reviewed. The nameplate provides crucial information, including the rated voltage, full load amperage FLA, locked rotor amperage LRA, and the minimum circuit ampacity. The full load amperage represents the current the motor draws under normal operating conditions. The locked rotor amperage is the current the motor draws when it's initially starting, which is significantly higher than the FLA. The minimum circuit ampacity is the minimum allowable ampacity for the conductors supplying the motor, typically calculated as a percentage of the FLA. Secondly, conductor ampacity needs to be addressed. The conductor ampacity must be sufficient to carry the calculated load. According to the National Electrical Code, specifically in EC section 430.22, the conductors supplying a motor must have an ampacity not less than 125% of the motor's full load current rating. This ensures that the conductors can handle the continuous load of the motor without overheating. For example, if the motor's FLA is 12 amps, the conductor ampacity must be at least 12 amps times 1.25, which equals 15 amps. Therefore, the minimum conductor ampacity in this case would be 15 amps. Thirdly, overcurrent protection needs to be addressed. Overcurrent protection is crucial to protect the motor and conductors from overloads and short circuits. The overcurrent protection device, such as a circuit breaker or fuses, must be sized appropriately. The NEC provides guidelines for sizing overcurrent protection devices for motors. According to NEC section 430.52, the maximum rating or setting of the motor's overcurrent protection device depends on the type of motor and the type of overcurrent protection device used. For an inverse time circuit breaker, the rating typically should not exceed 250% of the motor's full load current. For example, if the motor's FLA is 12 amps, the maximum circuit breaker size would be 12 amps times 2.5, which equals 30 amps. However, the actual circuit breaker size may need to be smaller based on the specific application and the motor's characteristics. Also, you have to review the wire size. Number 12 THHM wire has an ampacity of 20 amps under normal conditions, as per NEC table 310.16. However, the ampacity of the wire must be derated if it is installed in certain conditions, such as in a conduit with other current-carrying conductors or in a high-temperature environment. Derating factors are provided in NEC table 310.15b3 for the number of conductors in a raceway or cable, and in NEC table 310.15b2 for ambient temperature correction factors. For example, if there are 4 to 6 current-carrying conductors in a conduit, the ampacity of the conductors must be derated to 80% of their rated ampacity. If the ambient temperature is higher than 30 degrees Celsius, the ampacity of the conductors must also be derated. If the number 12 THHN wire is installed in a conduit with 4 to 6 other current-carrying conductors, its ampacity would be reduced to 20 amps times 0.8, which equals 16 amps. This derated ampacity must still be greater than or equal to 125% of the motor's full load current. Furthermore, regarding voltage drop occurs when the voltage at the load is less than the voltage at the source. Excessive voltage drop can cause the motor to overheat and malfunction. The NEC recommends limiting the voltage drop to no more than 5% from the source to the load. To calculate voltage drop, you need to know the conductor length, the conductor size, the load current, and the conductor impedance. The voltage drop can be calculated using the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which is approximately 12.9 ohms for copper conductors, I is the load current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. For example, if you have a 100-foot run of number 12 copper wire carrying 15 amps, the voltage drop would be approximately 4.4 volts. If the source voltage is 208 volts, the voltage at the load would be 203.96 volts, which is within the 5% voltage drop limit. Moreover, short circuit current rating SCCR is important. The short circuit current rating of the S/C unit and its components must be sufficient to withstand the available fault current at the installation location. The available fault current is the maximum current that can flow during a short circuit condition. The SCCR of the equipment must be greater than or equal to the available fault current. If the SCCR of the equipment is less than the available fault current, the equipment could be damaged or destroyed during a short circuit condition. The available fault current can be determined by performing a fault current study. This study takes into account the impedance of the utility transformer, the conductors, and other components in the electrical system. The SCCR of the equipment is typically marked on the equipment nameplate. Regarding ambient temperature, the ambient temperature affects the ampacity of the conductors and the performance of the S/C unit. High ambient temperatures can reduce the ampacity of the conductors and cause the S/C unit to overheat. The NEC provides temperature correction factors for conductors installed in high-temperature environments. The S/C unit manufacturer also provides temperature limits for the unit's operation. It is important to ensure that the S/C unit is installed in a location where the ambient temperature is within the manufacturer's specified limits. On properly sizing the circuit breaker protects the wiring and equipment from overloads and short circuits. The circuit breaker must be sized appropriately to protect the wiring and equipment without nuisance tripping. Nuisance tripping occurs when the circuit breaker trips under normal operating conditions. The NEC provides guidelines for sizing circuit breakers for different types of loads. For motor circuits, the circuit breaker is typically sized at 125 to 250% of the motor's full load current, depending on the type of motor and the type of circuit breaker. Another point is coordination. Coordination involves selecting and coordinating overcurrent protection devices to minimize the extent of an outage during a fault condition. The goal is to have the overcurrent protection device closest to the fault trip first, while the upstream overcurrent protection devices remain closed. This helps to isolate the fault and prevent a larger outage. Coordination studies are typically performed by qualified electrical engineers. Finally, grounding and bonding are important for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protection device and clear the fault. Bonding connects all metal parts of the electrical system together to create an equipotential plane. This helps to prevent electric shock hazards. The NEC provides detailed requirements for grounding and bonding. In summary, while the existing 20 amp circuit breaker and number 12 THHN wire meet the minimum requirements, a thorough review of the S/C unit's nameplate data and a detailed calculation of the conductor ampacity of a current protection, voltage drop, SCCR, ambient temperature, circuit breaker sizing, coordination, and grounding and bonding are necessary to ensure compliance with NEC and to provide a safe and reliable installation. It is recommended to consult with a qualified electrician to perform these calculations and ensure that the S/C unit is wired correctly.